Well, welcome back to Lesson 7 in our study of network communication. The course is based on a text by Jim Caros and Keith Ross entitled Computer Networking, a Top-Down Approach. And we're taking a journey through the TCP/IP model from top layer to bottom layer. We've already visited the application layer and we've explored that. And now we're in the process of studying the transport layer. The transport layer's responsibility, as we have already learned, is to make sure that all those bits that represents the message that the application is trying to send makes it from the host to source all the way to the destination intact, without being lost, and in the right order. We've explored a couple of scenarios, one of them being that we're operating on a network that never loses bits, period. Well, that's not realistically. And then we started adding the real-time problems that exist in communication. And problem number one is the possibility that a bit could be changed or lost somewhere in transit, either along the link or perhaps in a buffer as it's being stored and passed from one router to the next. The question was, how does a sending unit know that the receiving unit got everything that was sent, or vice versa, how does the receiving unit know that it got the entire message correctly? And we found out that the transport layer protocol actually takes the message that came down from the application and added its own set of bits. It's called the header. And in that header, it has information that will help it to validate that data as it makes it from one end to the next. Information such as checksum value, a hash checksum that represents some sort of a mathematical operation on the bits, because they are zeros and ones, which means you can do math with them. And the hash operation on that set of bits generates a product that is stored in a field referred to as a checksum. And when the packet gets to the other end, the device at the other end runs that same hash operation on the bits that it received. And if it was correct and there was nothing lost, the product should be exactly the same that they get that is stored in that field. Now we're going to see a state machine or a series of state machines to represent this process. So let's pick that up. When we ended that last lesson, we had discovered that not only did the sending and receiving units have to determine somehow whether or not the message arrived with all the bits in the right order, but they also had to let each other know about it. And so they added another piece of information to the process, and that is an acknowledgement or a negative acknowledgement from the receiver to the sender, indicating whether or not the segment that was received matched the segment that was sent. And then we further discovered that not only did we have the potential problem of the segment being corrupted, but the acknowledgement and the negative acknowledgement might possibly be corrupted. And so we talked about a number of different scenarios to deal with that situation. So here we are now looking at a state machine that represents some of this process. This is RDT 2.1. And it says the receiver handles garbled, AX, and NAX. The RDT 2.1 sender and receiver state machines each now have twice as many states as before. This is because the protocol state must now reflect whether the packet currently being sent by the sender or expected at the receiver should have a sequence number of 0 or 1. Note that the actions in those states where a 0 numbered packet is being sent or expected are mirror images of those where the 1 numbered packet is being sent or expected. The only differences have to do with the handling of the sequence number. Protocol RDT 2.1 uses both positive and negative acknowledgments from the receiver to the sender. When a correct packet is received, the receiver sends a positive acknowledgement for the packet it has received. When a corrupted packet is received, the receiver sends a negative acknowledgement. We see from this slide a number of the issues we talked about last time, adding a sequence number to make sure that we can determine whether or not the packet being received is an original or a duplicate. We can accomplish the same effect as a negative acknowledgement if, instead of sending a negative acknowledgement, we send another acknowledgement for the last correctly received packet. A sender that receives two acknowledgments for the same packet knows that the receiver did not correctly receive the packet following the packet that was being acknowledged twice. This is our negative acknowledgement free reliable data transfer protocol for a channel with bit errors. One subtle change between RDT 2.1 and RDT 2.2 is that the receiver must now include the sequence number of the packet being acknowledged by an acknowledgement message. This is done by including the ACK0 or the ACK1 argument in the make package process in the receiver state machine. And the sender must now check the sequence number of the packet being acknowledged by a received acknowledgement message. This is done by including the 0 or 1 argument in isACK in the sender state machine. So let's take a look here. Taking a look at these state machines here. Here is the sender. It is waiting for a message from the application layer. The application layer sends a message and it does a make packet to create a new segment to send, and it sticks the acknowledgement 0 in the field, indicating that this is a response to the previous acknowledgement that it received from the receiver, which was an acknowledgement 0 indicating that it had successfully received the previous packet. And so it creates this and sends it across the line. Here is the receiver waiting for that message down below. Now let's say it comes in and it does not have an acknowledgement 0. It has something else. Well, that would indicate to this receiver that it is not getting the correct packet. So it doesn't do anything but resend the same acknowledgement that it sent previously. In other words, an acknowledgement 0. When that comes back up here, it receives an acknowledgement 0, although it's expecting to receive an acknowledgement 1. But it receives an acknowledgement 0, which is the same acknowledgement that it got from the previous successfully received packet, which tells it the receiver did not get the last packet correctly. So it retransmits it. Now let's say we're back down here and it's waiting for this retransmitted message, and it does come in this time, and this time everything looks good. So the receiver creates a new packet, that being a new acknowledgement packet, which has an acknowledgement 1 in it, which is different from the acknowledgement 0, which indicates that it successfully received the packet with 0 in it, and it's ready for another one. And it transmits that one. And when this thing comes back to the sender with the new acknowledgement 1, that indicates to the sender that the receiver got the last packet correctly, and now it will create a new packet to which it will stick that 1 and send it back again. So to repeat, when the sender receives that acknowledgement 1, then it creates this isACK, which includes that acknowledgement 1, which resets it to waiting for another call from above, except this time it would say waiting for call 1 from above, and the cycle starts all over. Well, that was not a terribly long lesson, but it was intense. So why don't we just cut it off right here before we go to RDT 3.0 and give you a chance to kind of study this a little bit and take care of any other business you may have. And when you feel like you've got it down, come on back and we'll go to the next one.